Hey everyone, welcome to this explainer. Today, we are unpacking a really groundbreaking paper. It's called Tracing Agentic Failure from the Flow of Success, and it tackles, well, literally, one of the most frustrating mysteries in AI right now, debugging. If you've ever watched an AI agent just completely lose the plot midway through a task, you absolutely know the feeling. Today we're exploring a radical new way to find out exactly what went wrong.
Think about the central mystery we face every time we build complex AI. The big question is always, why did the AI fail? When an agent is tasked with executing this massive multi-step plan and it ultimately crashes or just gives you completely garbage output, how do we figure out exactly where the plan fell apart? It is for sure like finding a needle in a digital haystack. Did it misunderstand the very first instruction? Did it grab the wrong piece of data halfway through? Or did it just trip at the absolute last hurdle? Okay, let's dive into this by tracing a typical workflow for an AI agent. Step 1, it analyzes the context. That leads right into Step 2, formulating a plan. Then comes Step 3, execution, and finally Step 4, the actual output. When that final output fails, this entire timeline essentially turns into a crime scene. And the real challenge? The error could be hiding anywhere. Like maybe the actual failure point was right there in Step 3, but the system didn't actually register a crash until Step 4. Trying to trace back through all these complex steps to find that exact, hidden moment of failure is incredibly difficult.
To solve this, we really need to ground ourselves in the exact terminology the authors use in the paper: failure attribution. Basically, failure attribution is the process of identifying which specific steps in a failure trajectory cause the LLM-based agentic system tasks to fail. It's not just knowing that the system broke, it's the precise pinpointing of the exact step or sequence of steps that triggered the entire domino effect leading to that failure.
So how are developers currently handling this? Well, it's not pretty. On one hand, we have prompting-based pipelines. This means you're constantly prompting the AI to double-check its own work at every single step. It's massively computationally expensive and, quite frankly, incredibly slow. On the other hand, we have step-level annotations. This is where human engineers actually have to sit down, manually go through failed runs, and tag exactly where things went sideways. As you can imagine, gathering that data is wildly costly and almost impossible to scale up. Basically, this traditional detective work, it's hitting a dead end. We desperately need a better way. And that brings us to the massive paradigm shift introduced by our authors. It's driven by this beautifully counterintuitive question. What if we only study perfect success? Instead of meticulously collecting failure data and agonizing over exactly where the errors happened and feeding all that negative data back into the system, what if we just completely ignored the failures during the training phase? I know it sounds a little crazy at first, right? How can an AI possibly learn to spot an error if it has literally never studied one? To really understand this, let's use the analogy of the perfect driver. Imagine you're in a car and you've perfectly memorized exactly what a flawless, smooth drive feels like. You know the exact rhythm, the balance around the turns, the steady hum of the engine. Because you know perfection so intimately well, you don't need to study 1,000 different car crashes to recognize when something goes wrong. The exact second the car swerves off the road or jerks unexpectedly, you instantly know there's a problem because it deviates from that perfect flow. The authors took this exact logic and applied it to AI debugging. Now, what's really interesting about this slide is how the authors translated this perfect driver concept into a real, lightweight solution called the OAT model. OAT stands for their approach to unsupervised failure attribution. And the word unsupervised is absolutely the key here. It means the model trains exclusively on successful trajectories. It doesn't need any step-level error supervision on failure data whatsoever. It simply learns the flow of success. Let's take a quick peek under the hood at how OAT actually achieves this mathematically. First, it uses a one-class learning mechanism, meaning, again, learning only from success. Second, it utilizes neural-controlled differential equations to continuously track how a process changes over time. And third, OAT models these successful trajectories in a latent space. So it's essentially building this hidden mathematical map of what a perfect workflow looks like from start to finish.
Okay, so we have our mathematical map of success. But what happens when the system actually encounters a failure out in the wild? Well, at inference time, when an agent system is given a task and it ultimately fails, OAT looks back at the trajectory. For every single step the AI took, OAT calculates what it calls an anomaly score. This score is based entirely on how much that specific step deviated from the learned dynamics of a successful trajectory. If a step strays too far from that flow of success, the anomaly score spikes and boom, It automatically flags it as the error step.
So the crucial point is just how incredibly efficient this learning process really is. You might think, okay, building a robust mathematical map of perfection must require millions of data points and weeks of training time, right? Actually, scratch that. It's way simpler. The authors found something astonishing. To train the OAT model effectively, it only requires 100 successful trajectories. That is literally it. Just 100 examples of the AI getting the job done right. This completely eliminates the need for all those massive, costly, human-annotated failure datasets we talked about earlier.
And the benefits of this lightweight approach are just absolutely staggering when we look at operational speed. The experiments conducted in this paper show that OAT operates anywhere from 200 to 5,000 times faster than those heavy, computationally expensive prompting-based baselines. Because it's simply checking an anomaly score against a learned mathematical model of success, rather than constantly pinging a massive language model to reevaluate its own logic over and over, the diagnosis is lightning fast. It is a monumental leap forward in efficiency.
And this brilliantly illustrates the ultimate victory of the OAT model. I mean, usually you expect a trade-off in computer science, right? If something is thousands of times faster and uses way less data, it kind of has to be less accurate. But looking at the F1 scores, which is a really precise measure of accuracy, OAT consistently outperforms the slower baselines. It boasts a massive 20% improvement in accuracy on in-domain datasets and even a 7% improvement on out-of-distribution datasets, meaning it handles entirely new, unseen tasks better too. It's faster, it's way cheaper to train, and it's significantly more accurate.
Which leaves us with a truly fascinating thought to wrap up this explainer. If we can trace agent failure so rapidly and so accurately just by mapping the flow of success, how will this framework change the entire future of diagnosing complex systems? We are finally moving away from the tedious, expensive, and heavy autopsies of thousands of failures, and moving towards simply teaching our systems the shape of perfection. It's a completely revolutionary way to think about AI debugging, and it opens up incredible possibilities for making our autonomous systems safer, faster, and much more reliable in the real world. Thank you so much for joining me to explore this incredible paper. Keep questioning, keep learning, and I'll see you in the next explainer.